Good afternoon, everybody. Welcome to I guess the final speaker in this logical session at A6101. You know that 101 is actually quite a good number. I guess if you watch the movie, 101 is a good one. Okay, so we are very pleased to have Professor Dean Longyun from Nankai University to give us a very good topic lecture, namely equivalence relations induced by policy groups. Professor Dean, please.
Okay, thanks to the organizer for invitation and thanks Professor Feng for introduction. Now, today, the frame of my talk is four parts. First, let's recall the definition of Borel reduction. Borel reduction is begin to introduce Borel reduction. Let's recall some notion of in descriptive set theory. First, polyspace. A polyspace is a separable, completely measurable topological space. So it means it's a topological space and it's homomorphic to a separable, complete metric space. But we don't mind the metric, which metric, the exact metric is. Okay, given two polyspace, we consider the Borel set. Borel set denoted by Bx. Bx is a sigma algebra generated by all open sets of X. So we can see that Bx contains all open sets or closed sets. These two class is the first level, and for the second level, it's F sigma. F sigma means countable union of closed sets. And G delta set is a countable intersection of open sets. This is second level. And for the third level, it will be G delta sigma and F sigma delta, and so on. So for G delta sigma, it means the set of countable union of G delta sets, and so on. This is the third level, but Bx can be split into infinitely many levels. Even more, this will be uncountably many levels. Okay. Now, the definition of Borel function. A function from x to y is Borel, means that the preimage of any open set is Borel. Okay, now the Borel reduction. Borel reduction is between two equivalent relations. Given two equivalent relations E and F on two polyspace X and Y respectively, we define E Borel reducible to F denoted by this notion. It means that there is a Borel function theta from X to Y such that for all xy in the space X, X and Y is equivalent by E if and only if theta X and theta Y is equivalent by F. So this means that if we know the Borel function theta, we know the equivalent relation F, we can say any property of E. So use this notion, it means E, the complexity of E is lower than F. Okay. Now we use this notion to means E and F are same complexity. It means E is reducible to F and F is also Borel reducible to E. And use this notion to denote that E is strictly reducible to F. It means that E is Borel reducible to F, but F is not Borel reducible to E. So use this notion, we can define a partial order on equivalent relations. Before going on, we need some more definition. Given a polyspace X, a subset of X A is said analytic or denoted by sigma 1, boldface sigma 1. If we can find another polyspace Y and a closed subset C in the X times Y, such that A, look at this definition. Here we can see that A is the projection of C. So analytic set is a projection of a closed set. And then co-analytic, denoted by pi 1. It means that A is co-analytic. It means that the complement of A is analytic. What's the relation between Borel set and sigma 1 and pi 1? Here is the most important theorem in discrete set theory, the Suslin's theorem. X is a polyspace, a subset of X A. A is Borel if and only if A is both analytic and co-analytic. Let's go on. Now, now we have the definition of Borel reducibility. Then let's introduce some most important theorem in the Borel reducibility. Here we need another notion. We say an equivalent relation E on X is Borel. We say E is Borel means that this set is a Borel set in X squared. And we say X is sigma 1 means this set is sigma 1 in X squared. And pi 1, the same thing. Okay. So the first dichotomy, Silver's theorem, say that let E be a pi 1 equivalent relation. It means this set is pi 1 subset of X squared. Then there are two cases. First is E is below identity of N. Another case is identity R is below E. Look at this. In the first case, we can see that there is only countably many equivalence classes. And if the second case hold, we see that at least we can find there is there are uncountably many, there are continually many equivalence classes. So here we can see something concerning CH. Okay, let's go on. So in this diagram, we use the dot to denote an equivalent class. And a line between two dots means the lower one is below reserved for the higher one. If two equivalent relations is bireducible to each other, we put them in same dot. Okay, let's go on. So the first dichotomy say that there is no equivalent relation between this point and this point. So there is no equivalent relation is on this line. The first. Now, the second dichotomy theorem. Second dichotomy theorem concerning equivalent relation denoted by E0. E0 is an equivalent relation defined on this space. This space, we call it counter space because it's homomorphic to the counter set. Okay, so with here X and Y is in this space, so X and Y is a sequence of 0 and 1. So X and Y are equivalent to each other if and only if their Xn equal to Yn for large enough n. So there are only finite remaining n such that Xn not equal to Yn. Okay, we can easily track that E0 is below bireducible to R over Q. R over Q means that to a real number is equivalent if and only if the difference between these two numbers is a rational number. This fact is trivial. Now, the second dichotomy say that let E be a Borel equalization. Then either E is below identity R or E0 is below E. So it means that there is no equalization between these 2 points. This is the second dichotomy. Let's go on. The third dichotomy. Third dichotomy concerning equalization denoted by E1. This line is the same one. This is the same as E0. Difference here is not sequence of 0 and 1. It's a sequence. Here, x1 are sequence of real number. Here, we use this to denote, define E1. We can easily see that E1 is the R to N over C double 0. C double 0 is this set. This notion is come from functional analysis. Okay. Now, the third dichotomy say that if we already know that E is below E1, then there's 2 cases. One is E is below E0, or otherwise, E is below bireducible to E1. So it means that there is no equalization between E0 and E1. Here is a dichotomy. But now it's not lines like this, like here, because we are going to the fourth dichotomy. The first dichotomy will consider equalization of E0 to omega. So we need to define E to omega. Here, E is an equalization on X. Then the E to omega is on X to the N, defined by this way. It means that X and Y are equivalent if and only if Xn is equivalent to Yn for any N. Then we only need to consider E0 to omega because E0 is below bireducible to R over Q. So E0 to omega is below bireducible to R to the N over Q to the N. Oh. Now, the fourth dichotomy. The statement of the fourth dichotomy is similar as the third one. So it means that there is no equalization between this point and this point. So first dichotomy here, second, third, fourth. All these dichotomies say that there is no equalization between 2 points. We know there are some other dichotomies, fifth, sixth, and seventh dichotomy, but they are too complicated. Today we don't talk about other dichotomy. Let's go on. Now we are going to introduce sequence equalizations. What sequence equalizations? Here we consider the space is R to the N, and if G is a Borel subgroup of R to the N, then the Borel equalization R to the N over G is defined by X and Y are equivalent if and only X minus Y is in G. This is so-called sequence equivalence relation. So E1 is for E1, G is C double 0. For E0 to omega, G is Q to the N. And we can consider some G, which is some Banach space. Here, C0, C, LP, L infinity. In functional analysis, with C0 and C are isomorphic. So we don't need to consider C but the equivalent relation is different. R to the n over C0 and R to the n over C is different. So we'll talk about the difference between C and C0 later. Here, for LP, it's just it's like list form. So it is increasing where as P increasing. How about C and C0? Okay, let's consider C0. All these LP equivalent R to the n over LP and R to the n over C0 are incompatible. And E0 of omega is strictly below C0. And C0 is strictly below C. So we have this. Here is LP, and here is C0 and C. Here we omit R to the n. Here LP means R to the n over LP. C0 means R to the n over C0. Let's go on. Another important equivalent relation is identity plus. Identity plus is an equivalent relation defined on R to the n. It means that here xy, both x and y are sequence of real number. We say they are equivalent if the image of x and y are the same. Now, the fact is E0 to omega is below. Okay, we just going on to the diagram. Here we can notice that identity is a closed equivalent relation. E0, E1, LP, L infinity is F sigma equivalent relation. And the following E0 to omega, C0, C, and identity plus is F sigma delta. So here is the identity plus. This branch, and this branch, they are all incompatible. Now, we wish to introduce so-called orbit equivalent relations. Given a Polish group, the definition is a topological group. Topological group means it's a topological space and also a group. And the group action, is continuous. Now, if a topological group whose underlying space is Polish, it means the topology on G is on this group is Polish space. Now, given a Polish group and a Polish space, we can define an action. And given an action G over X, action is a mapping from G times X to X. If we're given a continuous G action on X, then we say X is a Polish G space. Now, given a Polish G space, we can define an equivalent relation named orbit equivalent relation. X and Y are equivalent if and only if. We can find G in a group such that G act on X equal to Y. This means X and Y are in the same orbit, so it's named orbit equivalent relation. We can easily see that all orbit equivalent relation is sigma 1 equivalent relation. Now, here. So, equivalent, here is the, this point is the most complete one orbit equivalent relation. And this point we denote the most complete one analytic equivalent relation. But today we don't need this point and this point. We only notice put attention only on here. Okay. After recall these facts, it comes a question arises naturally. Can we say something on the Polish group G? Can we characterize the Polish group G by the where the Borel reducibility between orbit equivalent relation EGX? Of course, we can do this, but today we'll introduce because you can consider all equivalent relation induced by Polish group G and so on. There's many results, non-results on this topic. But today we'll introduce one equivalent relation for one group. Before we're doing this, we shall recall some subclasses of Polish groups. TSI and CLI. Given a group G and a metric D on G, we say D is left invariant if we DGH equal to DHK for all GHK, and right invariant if we put G in the right side, and two-side invariant if D is both left and right invariant. Now, for a Polish group, there is a theorem, Birkhoff-Kakutani theorem, say that for any Hausdorff-countable topological group, we can find a compatible left invariant metric on it. So, for a Polish space, for a Polish group, Polish group means we can find it's a Polish space. So that is a complete, several complete metric on G, and this theorem tell us that there is another metric which is left invariant. But can we find a metric D is both left invariant and also complete? In general, we cannot find such a metric, but if such a metric exists, we say this group G is CLI. CLI means complete left invariant CLI. And TSI. TSI means that there is a compatible two-side invariant metric on G. Here we didn't say complete, because for a Polish group, all two-side invariant metric is complete. Okay. So we get two subclasses of TSI and CLI. Now, by the definition, we can easily see that all abelian Polish group is TSI. And we can easily prove that all compact Polish space, the Polish group is also TSI. And by the definition, we can see that TSI is a subclass of CLI. Then we can easily prove that locally compact Polish group is CLI. But in the following, we'll claim that CLI is far more complicated than locally compact. Okay, we also need the definition of Lewis product. Here is the definition of Lewis product, but you don't need to notice that. To notice the definition here is too complicated. Anyway, you can find Lewis product on the internet easily. A fact is that if here lambda is a countable group and G, then the Lewis product is CLI if and only if G itself is CLI. Another subclass is so-called non-archimedean. Here we need a notion of S infinity. I think everybody knows Sn, the permutation on n of n. But here, S infinity is the group of all bijection from n to n. And the topology is the point-wise convergence topology. This is a Polish space, a Polish group. And for any group G, we denote identity element by 1G. Then let G be a Polish group, then the following are equivalent. First, G has a countable neighborhood base at the identity element consisting of open subgroups. Second, G is isomorphic to a closed subgroup of S infinity. So, for both these, indeed we say we'll use the first clause to define non-archimedean, and use the second one as a theorem, as an equivalent condition of non-archimedean. Okay. Now we are going to define an equivalent relation for any Polish group. This here is the definition. Given a Polish group G, we define E of G on G to the N like this, but X and Y are sequence in G. Then we say X and Y are equivalent if and only if Xn Yn inverse is converged in G. We say this EG is the equivalent relation induced by G. Okay. We can denote CG is a subgroup of G to the N, which is all such X such that Xn is converged in G. If G is a Polish group, we can prove that CG is also a Polish group. Then the equivalent relation EG is G to the N over CG. So we have this. So we can see that here an equivalent class is a right coset. Right coset of CG. Okay, the most simple one is if we put G is the real numbers, this group real numbers. Then here CR is just the C, the Banach space C. Okay, here we will claim that EG is an orbital equivalent relation induced by CG act on G to the N. Here the action is just the left multiplication of CG on GX. So we can see that EG is an orbital equivalent relation. Let G be a Polish group, then CG is also Polish. And if G is CLI, so CG is also CLI. If G is TSI, CG is also TSI. If G is non-archimedean, CG is also non-archimedean. All of these are trivial facts. Another trivial fact is that let G and H be two Polish groups. If G is topological isomorphic to a closed subgroup of H, then we can easily see that EG is below reducible to EH. Now, let's give some non-trivial results. Okay. We have recalled some so-called benchmark equilibration. So we compared EG with the benchmark equilibrations. First, let G be a Polish space, then G is discrete countable group containing at least two elements, if and only if E.g. is Borel bi-reducible to E0. Second, G is psi uncoupled non-archimedean if and only if E.g. is Borel bi-reducible to E0 omega. And for the identity plus, E S infinity is Borel bi-reducible to identity plus. And G is non-Archimedean if and only if EG is below identity plus. This is some EG natural fact. Okay, then in the following we'll use some theorem. For example, we'll use so-called right yield compatibility defined by Lupini-Panacchio topology. Let G and H be two-poly group. If H is CLI, but G is not CLI, then EG cannot is not below to any EHY for any Polish H space. Here, then in particular, we can get this because for EH, the EH is an action of CH. And by the non-fact, if H is CLI or H is CLI, then so is CH. So use this fact, we can get this because we can put CH here. Then we get EG is not reducible for EH. So if H is CLI, G is not CLI, EG cannot reducible to EH. So the Borel reduction can tell me which group is CLI and which is not. Now, for the non-Archimedean, we get the same similar result theorem here. Here we use some notion so-called turbulent and CZ equality defined by Farah. Let G and H be two poly groups. If H is non-Archimedean, G is not, then EG cannot resolve to any EHY. And we put CH here, we get this result. So this theorem and the last one theorem is similar. But this one tells me how to characterize non-Archimedean. Okay, let's go on. Here is a very complicated notion of alpha unbalanced defined by Allison and Panacchio topology. You don't need to look at this. Just ignore it. Use this definition, we define another notion. So we say a group is alpha unbalanced by this blah, 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 blah. You just ignore it. Let's go on. Here, omega 1 is the least uncountable ordinal. Let G and H be two Polish groups, and alpha is less than omega 1. Here, this means alpha is an uncountable ordinal. If G is alpha unbalanced, but H is not, then EG cannot resolve to EH. So we can use alpha unbalance to characterize the Polish group level by level, but does them exist? So we need some example. First, all TSI Polish group are one unbalanced. Are not one unbalanced, sorry. And if G is non-CLI, then it's alpha unbalanced for any alpha. Even alpha is bigger than omega 1. Because in the definition, we require that alpha is less than omega, but here, the definition also works for alpha larger than omega 1. So, okay, that's it. So, can we find more examples? Now, a topological group G is distal. The definition is here. If for any non-identity element H, conjugation of H cannot convert to identity element. This means identity element is not in the closure of all these set or all these elements. A known result for distal is that all TSA polygroups are distal, and also all Nilpotent polygroups are distal. Now, if G is not distal, then G is one unbalanced. Particularly, if we already know that G is locally compact, then G is not distal if and only if it's one unbalanced. So there are many examples of one unbalanced. Now, for locally compact, if G is locally compact, G is not two unbalanced. So locally compact we can only go up to 1 and cannot go to 2. Then, now we use the race product. Here, if lambda is an infinite countably discrete group and alpha less than omega 1, then G is alpha unbalanced if and only if the race product is on alpha plus 1 unbalanced. So we can use the race product to get higher and higher level of unbalance. But we can this level we can only plus 1, plus 1, plus 1, so we get any natural numbers level, but we cannot get the omega unbalance. Indeed, so far we didn't find any example of omega unbalance. Okay, so the story here now, this section is between E0 omega to identity plus. It's on this line. Here, there is no dichotomy. All dichotomy is here, but we don't know any. Here is very, very complicated between these 2 points. Now, how about these 2 points? Let's go on. Last section, we'll talk about TSI Polish group. Let G and H be 2 Polish groups. If H is TSI but G is not, then the same thing happened. E.g. cannot resolve to EH. More than this, let G Polish group, then the following are equivalent. First, EG is below C0, and EG is below E0 omega, and G is TSI non-archimedean. These 3 is same. So that means we can, so here we can see that there is no EG between E0 omega and C0. But how about C? We know that C is above C0, but we just guess maybe this hold, but I don't know the answer now. So here we see that there is no equivalence between E0, no EG between E0 omega and C0. But Farah has proved that there are many and many Borel equivalent relations between these 2 points. Okay, now how about here C0 and C? We don't know. It's an open question now here. And in the following we saw about some equal EG is above here because this point is just E of R. Now we consider some complicated group length R. We need another notion, so-called no small subgroup. We say topological group has no small subgroup, or is NSS here, NSS. If there is an open neighborhood of identity such that no non-trivial subgroup of G is contained in V. This means that for any G, if is not identity, then there is an M such that G or G to M is not in V. We generalize this definition to so-called strongly NSS if there is an open set of V such that for any sequence in G, if the sequence is not converged to identity, then we can find finite remaining n0 to nk such that G n0 to G nk is not in V. Now, we get the main theorem for TSI Polish group. Here, given Polish group G, we use G0 to denote the connected component of identity element in G. Then, let G be TSI and H be a closed, this condition is very, very complicated. H be a closed subgroup of the product of this HM, sequence of HM, and this HM, each HM is TSI and strongly NSS. Now, if EG reducible to EH, then we can find a continuous homomorphism S from W to H. What's W? Here, the kernel is non-archimedean, and W is a subgroup containing bigger than G0, and W, what's W? W is a countable intersection of clopern subgroups in G. So this term is a little bit complicated. Moreover, we say that the converse is also whole. One is whole if here G is just W, and the image SG is closed in H, and the interval can be embedded into H. So here H should not be described. So we call it the main theorem, but it's too complicated. So we'll use this theorem to some special cases. First, we'll talk about so-called plurality. What means plurality? Okay. A topological group is Lie group. We will not give the definition of Lie group. I suppose everybody knows it. But there is an equivalent relation. There is an equivalent condition of Lie group. A topological group is a Lie group if and only is locally compact and NSS. No small subgroups. Okay. Now, if H is locally compact, then H is strongly NSS if and only is NSS. And a Lie group is Polish if and only if it is separable. Separable means if and only it has at most countably many connected components. Now, we will use these conditions on the condition of H here. So H is TSI plurality. TSI plurality means that H is H is a topological isomorphic to a closed subgroup of the product of sequence of separable TSI Lie groups HM. So use this condition, we can see that such H is this kind of H satisfies this requirement. So we can use the main theorem on TSI plurality groups and get a rigid theorem for locally compact TSI plurality group. Let G be a locally compact connected TSI plurality group. H be a TSI plurality Polish group. Then EG plurality to EH if and only there exists a continuous homomorphism S from G to H such that the kernel is non-archimedean. This is the first rigid them. And particularly, we use rigid them on TSI Lie groups. Because TSI Lie group is all Lie groups are locally compact. So let GH be two separate TSI Lie groups, such that G is connected. Then EG resolves EH if and only if we can find an continuous locally injective homomorphism S from G to H. Here, the kernel S is non-archimedean because G is Lie group. Lie group is NSS. For NSS group, the non-archimedean means discrete. So we can find a continuous locally injective homomorphism. As a corollary, we use G and H on this very simple Lie group. R to C0 times T to the C0. Here T is TT is the group of complex numbers with norm 1. Okay. So this group this equivalence if and only if E0 is less than E1. This means the torsion in first group is no more than is less than no more than the next one. And here C0 plus E0, C0 plus E0 is the dimension of this group. So the second condition means the dimension of the first one is less than the second one. Okay, we also use the main theorem in the Banach space. But for separate Banach space, when it's strongly NSS, that is a very simple condition. X is not strongly NSS if and only if it has a closed linear subspace topologically isomorphic to C0. So C0 is the typical not strongly NSS space. Now, with the theorem for Banach space, let Xy be two separate Banach space such that Y contains no C0, copy of C0. So this means Y is not strongly Y is strongly NSS. Then, if Ex below resolves EY, if and only if X is topological isomorphic to a closed linear subspace of Y. Here, we don't know how to analyze the condition of strongly NSS. Okay, so at this section we talk about Polish group TSI is over this point. Here, maybe. Okay, that's all. Thank you.
Thank you, Professor Ding, for the very nice talk, and he explained in a very friendly way. Is there any questions or comments? Maybe you can have free discussions with Professor Ding.
Yes, we can discuss after the talk.
Yes, anytime.
Because after the talk, we can speak in Chinese.
Okay, so if no, we stop here and you can discuss freely with him. Thank you.
Thank you.